So we'll continue reviewing for the final exam as we were doing yesterday. We covered everything on chapter 7. So we did inverse tricks, logs, exponentials, L'Hopital's rule, and wrote the functions. And we started talking about integrals. So we'll continue doing integration today. And since we had already reviewed chapters 13 and 14, I'm going to try to emphasize the previous chapters. So 7, 8, 10, 11, and 12 over 13 and 14 that I think we covered quite well in the last month or so, plus we just had an exam. So I'm not that concerned if we don't have enough time on Thursday, our last day, to go over everything on chapter 13 and 14. That is, unless you have specific questions or concerns that you would like to address, then we can certainly change that plan. But for now, I think it's better if we look at the harder sections, in my opinion. I mean, certainly the other integration for sure. So let's continue. Let me show you our plan. So we have done chapter 7 already. We did integration by parts. So let's continue over all the other techniques of integration today. And we'll then hopefully start talking about sequences as well, okay? So let's turn to the set of problems. And remember, if you have any specific one that you would like to talk about, let me know. And then we can take a look at that one as well. All right, so let's go page 2. We're gonna do some integrals, and we had already worked on the integration by parts problems. So today, let's take a look at these trigonometric integrals. And they generally come in 2 flavors. We either have the ones that are products of sines and cosines, like let me just, like these ones, right? These are products of sines and cosines. Or we have the ones that have secant and tangent, like these ones over here. This is generally the case. Now, if you have sines and cosines, there are 2 particular ones. You have easy ones that where one of them is odd. Those are the preferred ones. So if one exponent on top, if one of the sines or the cosines that appears in the numerator, in the top of the fraction, is odd, we're in business, right? So those are easier. And so that would be like these ones over here. And these would be considered easy, these green ones here, because we have an odd number on top, cosine to the 5th or sine to the cube. If both of them are even, those are the hard ones. All right, so this one over here would be considered hard. And then for secant and tangent, you can either, it's a little bit different. If the tangent is odd, then it's good because you can extract the secant tangent. So this one would be considered easy as well. So just make sure you check them out, the general process. And let me do one here, for instance. So let's do 7. Let's do something like, what would be a good thing? Well, let's do B and C. Or at least make them into integrals that are now easier, right? Maybe I won't complete them, so we can do more stuff, but at least do the hard part, so to speak. So this is, let's do 7b, the integral of sine cube cosine square x, and the bottom dx. Let's turn to the page. Okay, so because this one is odd, so odd, and odd means we are happy because it will be easy. The thing you want to do is extract one of them. So write sine square sine x dx divided by cosine square x. And you want this to be your du. So you want this part to be du. And that suggests to you what the u should be. So the u should be, in this case, well, negative cosine, but let's just make it cosine. So cosine x, there's no reason to carry around the negative sign. This makes it more complicated. So if u is cosine, then du is negative sine x dx. Okay, and then so then you change everything, and this cosine immediately works here, and it doesn't quite work here, but then you use the sine square plus cosine square equals 1. So this becomes 1 minus cosine square x divided by cosine square x times negative sine x dx. And I'm going to put another negative sign outside to kill this negative sign that I put it here. And I did it so you can see how everything can be replaced now. So this part is du. This is u squared. This is also u squared. So my new integral is 1 minus u squared divided by u squared du. And this you can do, right? You can do 1 over u squared, that's u to the negative 2, and u squared over u squared, that's 1. So do this and then change u equals cosine, all right? So finish it. Okay, we'll leave it there so we can do more, okay? So that's if you have an odd one. If you don't have an odd one, like the other one we had, I believe was sine square x, cosine square x. If both are even, so here, both even, and that's bad. And if it's bad, then what you want to do is you want to use the half angle identities. So here what you want to use is that cosine square x is 1 plus cosine 2x divided by 2, and sine square x is 1 minus cosine 2x divided by 2. That's what you want to do, all right? So we do that, plug these two there, so this will be 1 plus minus divided by 2 times 1 plus cosine 2x divided by 2. You multiply it out, so the 2 and the 2 can come out as a 1/4, and this is a difference of squares, so this will be 1 minus cosine square of 2x. And look here, again we got a bad one, right? It's even, so it's again bad, so we use it again. So this time the one you want to use is, the difference is that now it has a 2x. So now cosine square of 2x is actually 1 plus cosine of 4x, right? Because there's a 2 here, now this is going to be a 4. So I can continue, and this is going to be 1/4 the integral of 1 minus all of these. 1 plus cosine 4x divided by 2 dx. Now I can simplify this. This will be 1 minus a half is a half. And then the other is minus a half of cosine 4x. And now I can iterate. In fact, let's take the half out. So it will be 1/8 the integral of 1 minus cosine 4x. And now I'll iterate here. So the integral of 1 is x, and the integral of cosine 4x is sine 4x divided by 4. And plus a constant c, right? And that's it. So it's harder because you need to use the identity, and then it reduces into something where if you're odd, you can do it in an easy way, but if it's even, you need to use the identity again, and so on and so forth. So the larger the exponent, the harder. So if we replace this by 4s, it becomes a super long problem. Okay, don't expect something like that in the final exam. you only have a finite amount of time. Okay, so this was 7C, I believe. And let's take a look at another one. So we can do one that has secant. So how about this one? Secant x tangent cube x, so 7D. Good. So for those, you want to either leave a secant tangent. Your goal is to leave a secant tangent or to leave a secant square, right? Because the derivative of tangent is secant square, the derivative of secant is secant tangent. Here we cannot leave a secant square because we only have one secant. So our only choice is to leave a secant tangent. So that's what we do. We separate the secant tangent, secant x, tangent x, dx. Now what else do we have? We have a tangent square. And this suggests what the substitution should be. So we want this to be du. And we know that the derivative of secant is secant tangent, so that's what u is going to be. U will be secant, so then du is secant x tangent x. And then we're good with this part, but tangent square we can't change, so then we have to use the identity tangent square plus 1 equals secant square. And so this tangent square becomes secant square minus 1. So we rewrite it here as secant square x minus 1 times secant x tangent x. And then if we use this u substitution, we can replace it by u squared minus 1, and all of this is du. And from here, this one is easier, right? So finish it. We'll leave it here, all right? But that's how you deal with secants and tangents. You either extract a secant tangent or a secant square. All right, let's move it along. So we have plenty of other ones to check. So that takes care of the trig integrals. Now we move on to trig substitutions. So that's 8.4, like problem 8 right there. And these are also kind of straightforward, right? You need to know, well, the procedure is straightforward. It can be difficult. I'm not saying it can't. But the way you're going to be dealing with this is as follows. If what you need to remember is the substitutions you are supposed to do. So here is what you should remember. If you have a squared minus x squared, you make x a sine theta. And you need to remember here that 1 minus sine squared is cosine squared. That's the identity you're going to use. If you have a squared plus x squared, then you're going to use a tangent theta. And here what you need to remember is that 1 plus tangent square is secant square. And if you have x squared minus a squared, you're going to use a secant theta. And the identity you need to remember is that 1 minus secant square is tangent square. What? Sorry, secant square minus 1. Okay, so that's how you do them. So let's pick one of these. For instance, this one. So again, maybe we won't complete the problem. We just write it. So this is 8a. Is the integral of 1 over x square root of x squared plus 1. And what we're going to do is look at the transformation we need. So we have x squared plus 1. So we're in the middle case, and with a 1, right? A is 1. So we're going to use x tangent theta. So what we use, x tangent theta. So then dx is secant square. Put it in here, dx is secant square. In the bottom we have tangent. and then square root of tangent square plus 1. And here's the beauty, right? Tangent square plus 1 is secant square. So this part is secant square. And so with the square root, you cancel it. So now you have secant square, tangent, secant, just a single secant. Then you simplify it. And so you have secant on top, tangent in the bottom. And then you're ready, you need to now solve this new integral, which at least has the benefit of having no square roots, right? We won, because there is no square roots. So the way to do this one probably would be to change it to sines and cosines. So secant is 1 over cosine. Tangent is sine over cosine. So these cosines go away. So you end up having 1 over sine, which is cosecant. And this is one you should know, right? So there were some special ones that we had to know. One of them is secant and the other is cosecant, right? So this one you should know, right? So let me write it here. So the important ones is secant. The integral of secant is ln of secant plus tangent. And the integral of cosecant, I think is, what is it? Negative ln of cosecant plus cotangent, I believe, right? You can check in the back of the book. So these two are ones you should know. The advantage is that this being an exam that you take home, well, you can at your leisure check that you know how to do these ones, right? Let me see. I'm looking right in the book where they could be. Yeah, I got it right. So it's negative ln of cosecant plus cotangent. Yeah, I wrote it correct. So that's how you finish this one, right? You put it over here. It's negative ln of cosecant plus cotangent plus c. And then your goal to finish it is to take it back to the x, right? And for that is where we draw the triangle. So we do a little triangle here. With your angle theta. And you know tangent theta is x. So you make the opposite x the adjacent one. That way this is x squared plus 1. So this is because tangent theta is x over 1. And then now you can figure out what are cotangent and cosecant, right? So from here, cotangent is 1 over x, and cosecant it will be the hypotenuse over the opposite. So x squared plus 1 over x. And then you put those back in here, all right? I won't finish it up. I almost did, but you can do the rest. So that's the thing with these ones, right? So you first do the trig substitution, and then you get a trigonometric integral. So this section sort of includes the previous one, right? After you do the trig substitution, you need to still do a trigonometric integral. So there's still work to be done. Okay, so let's do the other one that was there. Let's do this one, the square root of 4 minus x squared. Okay, so for this one, we want to use, so now our substitution is, if I go to the top, it's like this one, right? It's a squared minus x squared, where a is 2 because it's 4 minus x squared. So over here, we're gonna use x equals 2 sine. So that dx is 2 cosine. And this integral becomes 4 minus 4 sine squared, and dx is 2 cosine. And this, of course, is 4 times 1 minus sine squared, which is cosine squared. So this is the integral of 4 cosine squared, which we will be able to simplify, times 2 cosine. So the square root of 4 is 2, so this is a 4. And the square root of cosine is just 1 cosine, with the other cosine is cosine squared. And then you need to do this one, right? And then now we're back to trigonometric integrals. How do we do this one? Well, we use the half angle identities, right? So this is supposed to be 1 plus cosine 2 theta divided by 2. You can now do it. So it will be a 2, 4 divided by 2, and then it's the integral of 1, which is theta, and the integral of cosine theta, which is sine 2 theta divided by 2 plus c. And then, of course, we need to go back to what theta stands for, right? So theta, you solve it from here. Theta is arc sine or inverse sine of x over 2. And then you can plug it in here. Okay? So that's how we do that problem. I'm going to leave it there. So I didn't finish it. Okay? Again, you need to complete it. And that takes care of trig substitution. Let's move it along. Next issue is partial fractions. Problems like this. Integrals like this of rational functions, right? Rational functions. And we have different procedures depending on whether we have something irreducible or not, right? And I don't, is there an irreducible one here? Let me see. I think so. These are all kind of maybe C. Okay, most of these are kind of on the easier side. So let's me try to do something a bit more challenging. I'll just invent one. And because I'm going to invent it, the numbers are not going to be pretty, right? So let's see if we have something like this. So in the denominator, I'm going to put x plus 4 and x squared plus 1. And 3x squared plus 7 on top. So it has to be rational functions. You need to make sure that the degree of the top is less than the degree of the bottom. If not, you need to do long division. Chances are that in the final you won't get that, but just to make you aware. So in here we're good because the degree on the top is less than the degree on the bottom. Then you should factor the bottom. In this case, I already did that work for you. And here we have one regular one and one irreducible one, x squared plus 1, right? X squared plus 1, we cannot factor it further. So that means it's irreducible. So then the procedure is to write down this one as a over x plus 4. That's a regular one. Had it been repeated, then you have to put b over x plus 4 squared, etc., right? If it had repetitions. And then this one, because it's irreducible, that one contains 2. You need to have the b and the c. Like that, right? Now you complete the, you put a common denominator here, which will be the product. And you multiply this times that, so that's 8 times x squared plus 1, and x plus 4 times bx plus c. And then you, because the denominators are the same, the numerators have to be the same. So 3x squared plus 7 has to be the same as a x squared plus 1 plus x plus 4 times bx plus c. Okay, and now you need to plug values of x to figure out a, b, and c. And some of them are good values. For example, if you have single linear factors, like this one, then those are great. So here plugging -4 works great. So plug x equals -4 will give me 3 times -4 squared plus 7 equals a times negative 4 is 16 plus 1, 17. And here negative 4 plus 4 is 0 times stuff. So I don't care, this will be 0. So this is negative 4 squared, that's 16 times 3, that's 48, plus 7 is 55, is 17a. So that means a is 55 over 17, right? Like I told you, because I just invented it, the numbers are not pretty, but that's good because then we get appropriate practice. So that's my a. Now more values, right? Now there aren't any more good ones because this is irreducible, but one that is always great is 0. So 0 is easy to plug, right? So then this will be 7. Here 0 plus 1 times a, so that's just a, plus 0 plus 4, that's 4. B times 0 eliminates it, and then it's just C. And the A is 55/17. So for C will be 7 minus 55/17. And this is 119 minus 55/17. Oh, I'm running out of ink. Yeah, okay. 119 minus 55. So this is 64/17. So that means C is the 16/17. All right. So we got A, we got C, we're still missing B, so we gotta plug another value, and then any number is as good as any other. The smaller ones are better, so I'm gonna use something like 1. So x equals 1 is easy to plug. So then this will be 10 equals 2a plus 5 times b plus c. And then you plug a and c. 2 times 55 over 17 plus 5 times b, which is the one we don't know, plus 16 over 17. Then I'm going to multiply by 17. So it becomes 170 equals 110 plus 5b plus 5 times 16, which is 80. Okay, so this is now 170 equals 190 plus 5b. So 5b equals 170 minus 190, that's minus 20. So b equals negative 4. All right, we got a number that is not as bad just by accident. Okay, so that's really the partial fractions part, right? Getting the a, the b, and the c. But then you still need to integrate it, right? So in now when we plug it, so the integral that we had that just invented is now the integral of a, which is 55/17 over x plus 4, plus the integral of bx, that's negative 4x plus c, 16/17 over x squared plus 1. And you still need to integrate these, right? And some are easier than others. For example, so the way to do this integral is to further separate it into more pieces. So this one will be 15/17 of dx over x plus 4. That's easy. Then the next one, I'm gonna take the negative 2, you'll see in a moment why, and leave the other as 2x over x squared plus 1. I'm doing that because what's the derivative of x squared plus 1? 2x, right? So that's great. And then the last one is 16/17 of 1 over x squared plus 1. Okay, so now we can integrate. This is ln of x plus 4. This, if you make u x squared plus 1, du will be 2x. So this is actually ln of x squared plus 1. And this one Careful, right? It's not ln of x squared plus 1, right? It's arctangent. And we're done. Okay, so careful about that, right? Don't believe that the integration is trivial. The integration is easy if you have linear factors. It's just ln. But if you don't have linear factors, you need to be careful, right? It can be an inverse trig function like this one, or something else. Okay, so that was a good one to try. The other ones, the ones that are here, don't have any repeated, irrational terms. Not irrational, irreducible. So that's why they're all kind of simpler. Oh, maybe this one, 10D. 10D was an example similar to the one we just did. Number 10, part D. Okay. So for the other ones, let's let's do another one where we just started. Something like B that has a repeated factor, right? So let's start B. So we have the integral of x plus 3 divided by x plus 1 squared times x minus 1. The degrees are fine. And now what you want to do is you want to write down, you want to write this as a over x minus 1. And now this one is repeated, so you want b over x plus 1 and c over x plus 1 squared, right? Because it's repeated. Then when you do the common denominator, this one I need to multiply by x plus 1 squared. This one I need to multiply by x plus 1 and x minus 1. And this one I just need to multiply by x minus 1. So now the numerators have to match. So x plus 3 has to be the same as a x plus 1 squared plus b times x plus 1 times x minus 1 plus c times x minus 1. And here the good numbers to try are -1 and 1 because those are the ones that make this 0. So let's try 1. When you plug 1, you get 4. 1 plus 1 is 2. 2 squared is 4. So that's 4a. When I plug 1 here, I get 0. When I plug 1 here, I get 0. That's awesome. So this tells me that a is 1. When I plug -1, I get 3 minus 1, that's 2. -1 plus 1 is 0. So that one is 0. -1 plus 1 is 0. And here -1 minus 1 is -2, so that's -2c. So this tells me that c is -1. And then I'm out of good values to plug. So now then you should plug any other one, and I like 0. So if I plug 0, I get 3 equals, this would be 1, so that's just a. This will be 1, and this will be -1, so that's minus b. And this will be -1, so minus c. And then you plug your a and your c. So my a was 1, and my c is -1, so this is another one. So now b is 2 minus 3, -1. And we're good, right? We were able to replace it. So now all that is left is the integration. So let's write it down. So the integral that we started with, I know you can see it right now, but I want you guys, I'm just copying the bottom one. It will be the integral of the a, where is the a, is 1 over x minus 1. So I'm copying this part. So it's 1 over x minus 1 plus b, which is -1, -1 over x plus 1, plus c, which is -1. So it looks like this, 1, -1, and -1. And you still need to integrate these, right? Now, again, same thing. The ones that are linear factors, they're easy. They're just the LNs. But this one is not linear, right? It's a square. So you need to be careful about that one. So that's minus the integral of 1 over x plus 1 squared. The way you're supposed to do this one is by writing it, I mean, do a u substitution, and then it looks like something to the negative 2 power, right? So if you make a u substitution, x plus 1, this becomes u to the negative 2. And now you can do it, right? It will be u to the negative 1 over negative 1 plus c, and that's plus 1 over u, so 1 over x plus 1 plus c. Okay, so be careful with the integration. I see a lot of you do the first part correctly, and then from here you say ln of this, and that's not right, okay? Don't get carried out because these are so easy, okay? Don't expect all of them to be equally easy. Good, so that takes care of the integration by parts, and I think that pretty much completes our integration techniques. So this on 10, it's like a combination of different ones for you to try. Like A, for example, it's probably an integration by parts problem. And so is logarithm base 2, right? You're supposed to do that one by parts. This is a partial fractions problem, and this is one where a simple u substitution will take you to one that you can do. Okay, then we also have improper integrals. So let's take a look at those. So improper integrals are integrals where you either have infinity or negative infinity, or a point where the function is not continuous in the interval of integration, right? So for example, here, the ones we have these that are simply with infinity or negative infinity. And then we have these other ones where the issue may be where we have a problem, right? So let's check where the problem is. So for the first one, this one here, the problem is where we divide by 0, right? And we divide by 0 when x is 1. So the problem here is when x is 1. So if x is 1, that's where we're going to be in trouble. This one over here, the second one, is where the denominator is 0, and that happens when x is 3. So here the problem is when x is 3. And that's the reason they are improper integrals, right? So improper integrals means you need to write them as limits. And then first do the integral with the correct parameters that you can do, and then take the limit to see if it actually works out. So we'll do one of each. So let's do I don't exactly know which one. About part B, B and D. So this is 11, I think it's 11. 11 part B. So 11 part B is the integral from 1 to infinity of 1 over x times x plus 2. Let's start with that one, and then we'll do D. Okay, so the way we do it is we change it to a limit when B goes to infinity from 1 to B. And now we're safe. So this is now an integral we're supposed to be able to do. Now, go and figure, this is a partial fractions problem, right? Now, this one is actually easy. I'm going to just write down the answer. I think this is just 1/2. So I'll write it. So if I do 1x minus 1 over x plus 2, you'll notice that it will be x plus 2 minus x. The x cancels, and you only get the 2. So to cancel the 2, I'm going to put a 1/2. Right? So I sort of did the partial fractions in my head. So if not, you can do it, and you will find that you're going to get the two numbers, 1/2 and -1/2. Really easy. I don't want to spend the time on that because I want to do the limit part. So let's move it along. So we integrate. The integral of this one is ln x. And the integral of this one is ln of x plus 2. And we're supposed to do it from 1 to b. So the first one is ln of b minus ln of b plus 2. And I don't need the absolute values because b is going to be big and positive. Minus ln of 1 minus ln of 3. Okay, let's simplify that. Ln of 1 is 0, for example. And here we can combine these two, ln of this minus ln of that, as ln of our fraction, b over b plus 2. And then minus times minus is plus ln 3. Right? That way we can do it. And now we can evaluate. See, we need to do it like this, because if you try to do the limit here, you're going to get infinity minus infinity, because both ln's go to infinity. But if you combine them like this, now you can do it, because this now goes to 1, right? When b goes to infinity, this fraction goes to 1. And ln of 1 is 0. This is ln of 1 plus ln of 3. This is 0, so this is ln 3 over 2. And we're done, right? That was 11b. So this one was convergent. This integral was convergent, right? Now let's do C. Take a look back at what it was. No, D. We wanted D. So the problem is in the middle. This is the integral from 0 to 5, 2 over x minus 3 squared. Okay, because the problem is at 3, right? We said that problem at 3. What we're supposed to do is we should split this integral from 0 to 3 and then from 3 to 5. And then do each one of these separately, right? And the good thing is if one of them fails, then the entire thing fails, right? So we don't need to do the other one. So I'm going to start with the first. So what is the integral from 0 to 3, 2 over x minus 3 squared? And we need to make a limit. It will be the limit when b approaches 3 from the left. And now this integral has no problem because it's from 0 to b, but b is not equal to 3. So we're good. Now we can do it. And the way we do it is we do a u substitution. So we set ux minus 3, du is dx. So this is the integral of 2u to the negative 2 du. And now the new parameters are when x is 0, u is negative 3. And when x is b, u is b minus 3. Okay? So this is, now we can integrate. The integral of this will be 2u to the negative 1 over negative 1, so it's negative 2. From negative 3 to b minus 3. So this is negative 2 over b minus 3 plus 2 over negative 3. Is that right? something's not right. I said it right, but I wrote it incorrectly. Negative b minus 3, right? I'm plugging b minus 3 in here. And then plus, when I plug negative 3 in here. Good. And then what about this limit? Well, if 3 approaches b from the left, this number will be a small negative number. And when I divide negative 2 by a small negative number, it becomes a gigantic number, right? So this goes to infinity. This is infinity. This part goes to infinity. So that means this interval is not convergent, right? And because this interval is not convergent, we're done. That's it. So this one diverges. And because this one diverges, this one doesn't work, then we don't need to do the other one, right? That's it. The one we want diverges, right? That improper interval does not exist. Now you need to be careful here. See, the problem is if you don't realize that it's improper, if they only tell you do this interval and you don't see that it's improper and you do it the regular way, you're gonna get a number because you're gonna integrate like we did here, and we're gonna plug it from 5 to 0, and you're gonna get a number, but that number will be wrong, right? Because this interval does not exist. So careful, very careful about that. Okay, so that finishes up our integration part, I think. Let me go back to our list of problems. So we did improper intervals. We did one of infinity and one where the problem is in the center. There's a few other improper intervals here of volumes as solid of revolutions. I'm going to skip that part because I don't think we're going to have any in the final exam, where you need to do a volume of a surface or revolution or you know, it's okay. You don't need to check this problem 12, okay? Instead, we can go to now sequences and limits. And first, the first ones are essentially just like limits. Disregard D, so there's no reason. Don't look at D. D you can skip. It's really so just forget about that one. That one you don't need to do. The other ones you should be able to do. They're relatively easy, right? But they're just like regular limits. So from here, see this one here, for example, A. You do it by the largest power in the top and the bottom, right? The largest power here is 1. The largest power here, it seems to be 2, but you have a square root, so it's really 1. So then you take leading coefficients, and it will be 1 and square root of 4. So this limit is actually just 1/2. Right? I just did it by looking at it. It's 1/2. Oops. 1/2. This one, it's a number smaller than 1. And when you take a number smaller than 1 and you raise it to larger and larger powers, it's like multiplying a number like 0.9 is 90%. If you do 90% and then 90% again and 90%, the number starts becoming smaller and smaller. So this one is also super easy. It's obviously 0. This one is 0. Very easy. And the only one that is challenging here is this one. And for that, you need to do L'Hopital's rule, right? Because this one, when you plug it in, the fraction will go to 1, but the exponent will go to infinity, right? And because it's 1 to the infinity, you need to do it with L'Hopital's rule. This one actually will be E. So I'm not going to do it, but I just wanted to outline it to you. Instead, I want to take a look at 10.3. So starting with series, and right here in series, we have these ones that are either geometric. So all of these are geometric. This red box, they're all geometric, so you should know your geometric series. how to know when it's convergent or divergent, and find out the answer, right? Because here the question is, what is the sum? So this is, it's not about convergent or divergent. It's actually about knowing what is the answer. And that's generally a harder problem. We'll do one of these as an example in a moment. And the other one is these kinds, the other kind, and these are of the telescopic kind. So these ones you can do because they become telescopic, and because they are telescopic, you can find out what the answer is, right? So let's take a look, for example, at 14a. By the way, it may, so I'll do a different one, like 14a, so similar to 14a, to show you what can be difficult or different, right? So I'm going to do from 3 to infinity, like it says there. And I'm gonna do 1 or 4 divided by k times k minus 4. I'm gonna do it. Let's see. Okay, so I'm doing a different one to illustrate. This one. Okay, so first you need to try to find out if it's a telescopic sum or not. And to do that, you may want to use what you know about partial fractions, right? So the idea is you want to write these as a over k plus b over k minus 4. So it's a little bit like partial fractions, only it's discrete, right? But you do it the same way. So you want 4 to be a times k minus 4 plus b times k. And here there are easy values to plug. You can plug 0. If you plug 0, you get 4 equals negative 4a. So that means a is negative 1. And then you can plug 4. And if you plug 4, this becomes 0. And then you get 4 equals 4b. So b is 1. So negative 1 and 1. Beautiful. So then this series becomes a is 1 and b is 1. So I'm going to put the b first. So it will be 1 over k minus 4 minus 1 over k. Okay? And that's kind of like the other one was looking, right? So now you need to evaluate this one. And here's the thing. This is going to be telescopic. See, start writing a few terms and you realize. How so? Well, let's see. So if you do it all the way to, so let's start writing a few of the terms. You plug 5. What do you get? You get 1 over 5 minus 4. So that's 1 minus 1/5. Then you plug 6. So it will be 1 over 6 minus 4 minus 1/6. Then you plug 7. So it will be 1/3 minus 1/7. Then 1/4 minus 1/8. Then 1/5 minus 1/9. Then 1/6 minus 1/10, etc. Right? And the point that I'm trying to make is, look at this. This negative 1/5 is going to kill this positive 1/5 that comes later, right? This negative 1/6 will be killed by the positive 1/6 that comes later, and so on. So that's the telescopic part. So all the numbers are going to cancel, except these, the ones that are not going to cancel are going to be these, the 1/2, 1/3, and 1/4. All others will eventually cancel. So this negative 1/7 will, I mean, I have dot, 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 so you don't see it anymore. But this negative 1/7 is going to cancel with the one after that. So this one will go, and so will these, and so will these, etc. So the only ones that are going to survive are the first 4. So the answer is actually 1 plus 1/2 plus 1/3 plus 1/4, whatever that is, right? I'll explain it a different way. So if you don't want to do it this way because maybe it's unclear to you, here's a different way. You can look at the partial sum from 5 to n of these. And if you separate the partial sum is the sum from 5 to n of 1 over k minus 4 minus the partial sum of 1 through k from 5 to n. And I hope you can appreciate it better, right? Now let's write this down. What are these? This starts with 5. 5 minus 4 is 1. So this is 1 plus 1/2 plus 1/3 plus 1/4. And the last one is 1 over n minus 4. Whereas this one starts in 1/5. So it's 1/5, 1/6, and the last one is 1 over n. So when you do this minus that, lots of things cancel. So starting with 1/5, everything cancels, right? So the partial sum is gonna look like it's going to look like 1 plus 1/2 plus 1/3 plus 1/4. Everything else after that is gonna cancel with these ones. And then I have the last few terms. The last few terms are negative 1 over n minus 3, negative 1 over n minus 2, negative 1 over n minus 1, and negative 1 over n. In other words, the first 4 terms here survive, and the last 4 terms here survive. So that's my partial sum Sn. Now, what is the limit when n goes to infinity? Well, all of these guys are going to go to 0, right? So the only thing that's going to survive are the 1, the 1/2, the 1/3, and the 1/4. So that's why that's the answer, right? Okay. So I on purpose did a harder one than the ones you have there. So if you take a look at the ones we had on the book, so I mean I made it k plus 4. So the one that I had 4 terms. See, this one is only gonna have 2. And the one in part B is only going to have 1, right? So these two are way easier than the ones that I considered before. All right, so last, let's consider a geometric one. This, by the way, has to do with one of the problems we had on our exam. Let me see if I can show it to you. If you remember, what is it, exam 4 right here. This problem, oh, it's not in this test, it's on exam 3 actually. So I won't be able to show it to you, I don't have it open. But on exam 3, we had a problem like that, right? About one of these, and you had to figure out if what the sum was. So let's do one here. For example, let's do D. D is similar to the one we had on the test actually. And that will be the last problem we do for today for our review. So for D, we have a sum. I'll modify it a little bit so that you get to appreciate what happens. So I'm going to start it at 2. From 2 to infinity, 2 over 3 to the k plus 1. The one where I'm going to do that one, okay? So you should make it look like it's a geometric series. And the key is to make it a geometric series that starts at 0, right? That's the key. So first, take the things that are extras here. So what are the extras here? This 2 is an extra, so take it out. And one of the 3's is an extra because I have power k plus 1. So take one of the 3's out as well. And then all you have is now 1 over 3 to the k from 2 to infinity, right? That's the first simplification. Now, perfect. And in fact, I'm going to write it like this, 1/3 to the k. Because you want it as r to the k to be a geometric series. Now, the problem is that this one starts at 2. So but that's easy. So that means take 2 more out. So then take 2 of these guys out. So take 1/3 and another 1/3 out. And now it's going to be 1/3 to the power k minus 2, right? And this is, if I simplify it, it will be 2/27. And this, if we do a j substitution, we can make it look now so that it starts at 0. So we make j to be k minus 2. And if you do that, now if I write it with j, now j starts at 0. And now it's 1/3 to the j. And that's perfect because now we can use the formula, right? What is the formula? The formula is that the sum of r to the j from 0 to infinity is 1/1 minus r if r is between -1 and 1. So 1/3 counts. 1/3 is between -1 and 1. So this is 2/27 times 1/1 minus 1/3. This is 2/3, so that's 3/2. So the 2's go away, and this will be 1/9 is the answer. All right? That's how you're supposed to do it. So extract what you don't need as constants, and then make it so that it starts at 0, so that you can use your formula. That's the key. All right? So we're a little bit over time already, so I'm gonna stop soon, unless there are important questions that you may have. If not, we'll continue tomorrow. We still have 2 more days for reviewing for the final exam. Okay? I'll provide you more details about the final exam as I'm getting them. The coordinator is working on it. So I know that I think now it's going to be hosted on our Math 150B resources page. Don't worry about it. I'll put a link from our Canvas site so you know where you can download the exam and upload it. And I'm also waiting for confirmation on the time frame for the exam, if it's going to be 24 or 48 hours. So I'll let you know about all of that as soon as I know more. Okay? Any questions? Okay, very well. I see you guys tomorrow. We'll continue reviewing. Stay safe.